All right, so this is a continuation of that quiz 1 review video for this chapter. And the next one is a graph again. So we're going to need to go ahead and start graphing it once we identify our asymptotes and domain. All right, so just like with exponential, logs also have asymptotes, but they don't have horizontal asymptotes. They have vertical asymptotes, and those vertical asymptotes comes from the inside of the log, be it a natural log or a regular log. And remember, to find our vertical asymptote, we take that inside and we set it equal to 0. So 0 equals x plus 1, right? So that tells me x would equal -1. So my vertical asymptote is at x equals -1. And I can go ahead and plot that on my graph. And remember, they're opposites because logs and exponential really are basically opposites of each other. They're inverses. They're how we undo the other one, right? So because the exponential had a horizontal, then the logarithmic will have the opposite, which is a vertical. And then the opposite happens with domain and range as well, right? So in exponential, domain is always -infinity to infinity, but in logarithmic, range is always -infinity to infinity. So you need to remember that these are really inverses of each other, the logarithmic and the exponential. And since they're inverses of each other, you're going to have the opposite things happen. So opposite types of asymptotes. One has the horizontal, one has the vertical, and then the domain and range also switch. So the domain is -infinity to infinity for exponential, but the range is -infinity to infinity for any of the logs. So that tells me -1 will be part of my domain, so I should probably go ahead and graph this so that I know exactly what's happening with my domain here. So we have to use the natural log of x plus 1. Close your parenthesis, don't forget to do that, plus 3, and then graph it to see what's happening. Okay, so when I look at this problem, my domain, remember, is my x, so I'm looking left and right. That means it's going towards the positive x's, so positive infinity on this side, and -1 is the smallest. So this is -1 to infinity, and they both get parentheses because it will never actually touch that vertical asymptote. And then we need to go ahead and create our table of values again. So we need to create our XY chart. So let's go to our table. My errors are happening here, so we're going to start out with my first error. So -1 gave me an error. I always like to put the error in there because that gives the starting point. Then it is 0, 3, 1, 3.7 basically, 2 and 4.1, 3 and 4.4, 4 and 4.6. We should be seeing, okay, so I probably won't go much beyond that, but I could put in the 6 and 4.9. Okay, and then we can go ahead and graph those. So we have the error at -1, so at 0 we had a positive 3, 1, 2, 3, 1 and 3.7, 2 and a little bit above 4, 3 and about halfway between 4 and 5, 4 and a little bit higher than that, 6 and a little bit higher, but still not to the 5. So remember, again, it should never touch that, and then we keep going in this direction gradually. All right, so the last page here, number 8, was one of the word problems. So we have to remember to decide which formula we're going to use to do this one. So your parent deposited $3,675 in an account when you were born to give to you when you turn 16. The funds pay 3.45% interest rate, compounded quarterly. So this is the big deal, right? How is it compounded? That tells you what type of formula you're going to use. Since it's quarterly, we're going to have to use that longer formula as opposed to the short one for exponential. So this one is A equals P 1 plus r over n to the nt. So again, we're going to have to think about what's my a, what's my p, what's my r, what's my n, what's my t. And remember that n is the number of times it's compounded each year. So when we say it's compounded quarterly, quarterly really means that it's going to get compounded 4 times each year. So that tells me that my n is 4. So the deposit, that's my principal, that's my starting amount. I'm going to take it out of my account on my 16th birthday, so that's my time, that's how long it was in there for. And then my rate here, remember, move it twice, so it'd be 0.0345. So then we can go ahead and plug it in. A equals 3,675, 1 plus 0.0345 over 4 to the 4 times 16. And then we can go ahead and type that into our calculator. So 3675, parentheses 1 plus. I'm going to use my fraction button here because I think it's easier. Arrow down to 4, out, parentheses to the 4 times 16. And we get 6367.3. Now again, remember this is rounding, so the 8 will make the 6 go up to a 7. So this is what A equals, and then we need to write a sentence. So I would say, on my 16th birthday, there will be $6,367.37 in the account. All right, number 9. All right, so in this problem, when I'm looking at it, remember the goal is to solve for x. Well, I can't solve for x right now because it's inside of the log. So in order to get rid of the log so that I can solve it, we're going to have to change it to exponential. Right? So to get rid, so that I can solve, we have to get rid of the log so that the x is not in the log. Just like if the x was in the exponent, we would change it to a log to get it out of the exponent so that we could solve. So remember, if there's no number here, that tells me that my base is 10. So 10 to the a, which my answer is 1, equals the 2x minus 12. Right? Because this was my base, equals my exponent. This was my original answer. Right? Because we always talked about this as log base b of the answer equals the x, which is my exponent. So I knew that my base was 10, my exponent is 1, and this is my answer. So 10 to the first power is 10. And then we can go ahead and solve this. So we would add 12. So we would get 22 equals 2x, divide by 2. So that tells me that x equals 11. And you also could always check this in your calculator, right? Because log base 10 is something that we can type in. So I could do log of 2 times, I think my answer is 11, minus 12. And it should equal 1, which it does. So we're good. All right, number 10. Well, the nice thing about number 10 is this is just like exponents, right? If my bases are the same, then my exponents have to be equal. So here, my logs with their bases are the same, so that means what's in the logs have to be equal as well. So I can just go straight to setting these equal. So then we would add 3x. So 7x minus 5 equals 23. Add 5. 7x equals 28. Divide by 7. And we have x equals 4. And again, well, this one, because the base is different, we're not going to bother typing that into our calculator. That's just our answer. All right, last one, number 11. Find the inverse. So remember, when we're finding the inverse, just like we did in the last unit, the idea is my original equation is really y equals 2 to the x. So to do the inverse, we have to switch our x and y. So x equals 2 to the y power. And now we need to solve for y. So if I'm going to solve for y, The issue is y is in the exponent. I can't have what I'm solving for as the exponent. So we are going to change this to a log to get y out of the exponent, because we can't solve for y if it's in the exponent. So remember again that whole idea, log base b of the answer should equal the exponent, right? So log, the base in this case is 2, the answer is x, equals my exponent, which is y. And now the nice thing is y is already by itself. I don't even need to solve any further. I just need to write it in inverse notation. So f inverse of x is equal to log base 2 of x. Don't forget to review other problems to make sure you're prepared for the quiz.